I'm Sean.
And I'm Cormac.
And Sean, tell me a little bit about your project.
Well, in the 1960s, two men called Dingle and Hughes independently carried out research on smaller vertebrates, including woodlice, and they concluded that, say, like a woodlice is put through a maze, for example, and made the forced turn in a maze, it will emerge from the maze turning in the opposite direction.
Hughes called this correcting behaviour, and this is where they got the title for the project. But nowadays, more commonly referred to as turn alternation or turn alternating behaviour.
In the initial stages of our investigation, we also took into consideration like environmental differences. So, for example, we tested the woodlice in bright, dark, damp and dry conditions. We found they moved quickest in the bright and the dry conditions, as this were most vulnerable to desiccation.
But the majority of the initial stages of the investigation were carried out on a 90-degree turn, sort of like this here. Whenever they were forced to make a right turn, and the majority of the woodlice would come out and display correcting behaviour by turning left.
Well, we also found that, say for example, a woodlice only had one antenna. If it only had a right antenna, it could only turn right, and if it only had a left antenna, it could only turn left, as this is where they could only feel the right and left sides, depending on what side they had their antenna.
After this, we thought we'd study the impact of walking the distance before a forced turn and the distance after a forced turn. So we varied it from 5, 10, 15 and 20 centimetres. And we found that the distance walked before the forced turn had little to no effect on the correcting behaviour of the woodlice. Whereas now we varied it again after the forced turn. We found the further and further away they got from the forced turn, the more likely the correcting behaviour was to be extinguished.
We also decided we were going to not only test them in a 90-degree angle, but also vary the angle sizes between 60 degrees and 30 degrees. And we used a photocopied protractor onto the page and placed the piece of wood onto the page like this and put the woodlice through. And we found out two very interesting things: that not only did they go in an opposite direction, but they also came out at a similar angle to what they were forced to turn.
After this here, we compared the behaviour of juveniles and adults. Well, we went by our own key, juveniles being anything under 8mm and adults being anything over 10mm in length. And we found that there was very, very little difference in the behaviour of the juveniles and adults. So this suggests it's a more innate condition, they're born in with it, sort of a survival mechanism which they've evolved to whenever they're living on land. This was our initial maze, and it was made out of Lego. It was very good because it's very easy to manipulate. We can change it into many different angles and shapes. But there was one big problem with it. The surface proved very, very problematic with the woodlice because it was very alien to them. They almost had to climb over it. So we moved on to this here maze.
This maze, the template came from a website called practicalbiology.com, and thanks to our technology department in the school, they made it on all these parts and everything for us. And basically, our initial test with this was just to see if the woodlice would show correcting behaviour in the maze. So we put him in at A2, and he had to go right at V and then left at W to show correcting behaviour. But after this, the majority of them did show. But we also decided if we could teach them a path. So we put them in at A2 and had to go right at V and right at W. And we did this about 20 times to repeat it. And then we took away the block here. And they still show correcting behaviour, which showed that they couldn't be taught. They couldn't be taught correcting behaviour.
Now we're just going to try and demonstrate this for you. We're just going to go for the basic experiment. We're going to go for a basic experiment.
Oh, you actually have woodlice here, have you?
This is a vivarium. This is where we keep the woodlice. It's a natural habitat. It's dark, it's damp, there's plenty of wood. As you can see, there's a lot of woodlice in there. It's moss and damp tissue paper. It's in very good conditions for them to live in. So now we're just going to, we're going to demonstrate just the normal forced turn.
Okay, go ahead, guys.
There's two woodlice there, a bigger one and a smaller one. We'll just take the bigger one for now.
The species is Procellio scaber, and they're just the common rough woodlice.
But they can't roll up in a ball, which is better for the experiments.
Maybe he'll be a bit more cooperative. No, it doesn't work 100% of the time. That's the thing about it.
He's going right here.
There you go, and that's correct behaviour for you. Well, thank you very much.
Any questions or?
Any questions?
That's absolutely fascinating, boys. How did you actually choose then the subject?
Well, whenever I moved house to Straver, we cut down lots of trees in our garden for firewood, and the thousands of woodlice then moved into this environment. And we started, this is what we based our investigation around, started Googling experiments with woodlice, and this is what we found and decided to use it. And there's like many aspects you can choose from to do it.
The initial research was just very basic. It was done in the 1960s by Dingle and Orion Hughes. And these here aspects, you know, the comparisons, the angles, the environmental conditions, we're just updating and rebuilding on it and adding our own points into it. So it's a great subject, and we hope to just continue the research again. Thank you.
Ryan.
And I'm Ronan, and we're from the Abbey Christian Brothers Grammar School in Newry in County Down.
Okay, Ryan, so tell us a wee bit about your project.
Well, it's an adaptive braking system to allow the car behind to make an informed choice whether it's a gradual braking manoeuvre or a sudden braking manoeuvre. This will be displayed through different lighting sequences based on the car manufacturer's design.
What made you choose this project?
Well, my teacher, Mr. Savage, came in our room and asked who wanted to do BT Young Scientist, and me and Ronan put our hands up, so that's how we wanted to do it.
Was there a particular reason for choosing this?
Well, I have a great interest in cars, so I really want to do something based on cars, and we just sat down together and came up with the idea of the adaptive braking system.
It seems to me maybe that this would be a project that would be of interest to some of the car manufacturers.
Yeah, well, we contacted several car manufacturers and we got replies from Mercedes-Benz and Renault, both expressing interest in our braking system.
How difficult is it to adapt what you have done to different types of cars?
Well, the adaptive braking system is adaptable to any brake-like design, so it should be no problem. Any car, any brake-like design, our braking system can be adapted into it.